So 10 of the biggest data breaches in history. This is just here. There's a little bit of scare tactic here. 2016, 3 billion records were made free at Yahoo out in the wild. It's a pretty scary thing. So every once in a while, if you've ever used Yahoo, you'll get something about, oh, your account has been found on the dark web. Well, that's why. And over the years, it looks like that was the worst year, but bear with me, we'll see some more slides. We have had, year after year, there's been these breaches where records have been lost. And so it's clear that it's a problem. So next slide. So this actually tells you what the dollar loss is. So this really gives you more of an indication of what's going on. So 2017, only 1.4 trillion. All right. So it's gone up and up and up. 2021, close to $7 trillion worth of losses because the data's been evaporated out of corporations. So pretty serious thing. Oh, all right. Well, it's not such a serious thing. Thank you.
Are they 2 trillion or
No, you're right. So, yeah, well, I just tack on a few zeros, right? All right. Still pretty large. Okay. All right. So most of that was due to the security world. In the privacy world, it's coming. So you can think about the privacy world as being about 2 decades behind the security world in terms of the technology and in terms of its impact on the world. So you're starting to see privacy things happen. Like some of these things are happening. So I wrote these out so I don't get the numbers wrong, right? Anyhow, so Sephora, I don't know if you've heard of them, $1.2 million. They're smaller than these other big names. Snap, 35 million. TikTok, 92, Google, 100, and Meta, 687 million. These are big fines. So what's happened in the privacy world is the fines have changed their character. So it used to be you would get a flat fine and it would be a slap on the wrist. So basically it was like considered a cost of business. And this is very similar to financial companies where they just write off fraud. And so like your credit card gets stolen, they actually don't really care because it's small enough that they can just write it off. Well, what's happened in privacy is, in particular, GDPR, which is European policy, European regulation, the fee or the cost or the penalty is a percentage of your revenue. So the numbers go up very, very quickly. And so this is why you're seeing these hundreds of millions of dollars of fines. Europe is ahead of us in terms of privacy, but in the United States, the regulations are happening statewide. So there's a thing called CCPA, which is a California one, which is passed recently, although it's not really being enforced yet, but it's coming as well. So I know this is coming to a theater near you, right? And you've seen it. You've seen it with some of the big companies. The smaller companies think, well, that's the big guys. It's not going to get to us. That's not true. It's like it'll trickle down.
Is there FTC enforcement and HHS enforcement for HIPAA?
Yes. So
there's some federal privacy.
Yeah. Now, so this is where the difference comes in that I kind of mentioned is regulations have been around for a long time. It's the fee structure that's changed. So people will either they're not afraid of the fees or they haven't been in the past or the penalties. And so now it's starting to matter because it hits them in the pocketbook, right? The same thing happened in security. Until there were big breaches, So, security was a necessary evil. You kind of just like, you didn't do it if you didn't have to, et cetera. Same thing with privacy.
So these are all EU funds.
The Sephora one is not. I think the Google and Meta one are. So
You say California's CCPA, is that a California law?
yes,
Okay, so that's not you.
that's right. So there's a California law and there's a few other that are on the way, but eventually all the states will have their own laws, which there really should be a federal law, but I don't even want to go there. Okay. Very commonly, security and privacy get mixed together as if they're kind of the same thing. Like when I talk to people about privacy, they're like, what part of security you work in? I don't work in security anymore. So this gives a good indication of they definitely overlap, but part of each has its own thing. So the blue bubble is about security. It's, security is all defense. It's kind of binary. It's either the bad guys are in or they're not. And so you've got defense in depth, which is like firewalls. You have data loss protection, not letting the data out. Security information and event management is more of the operational stuff, which I'll mention a little bit later as well. Very solid security things. Privacy is broader. There is this overlap. So if you look at the things in the overlap, these are examples. The first part of the bullet is really the way that privacy looks at it. And the second part is the way that security looks at it. So in the security world, your data has to have integrity. It's basically, it has to be kept sound. You can think about databases that they have to be consistent. You can't have corruption. It's essentially the same thing. Accuracy is more in the ballpark of privacy, where you need to make sure that the data that you have about an individual is accurate. So like if you have the wrong social security number for somebody, that's a problem in a privacy sense, because you get into different violations. For access and availability is a security thing where you've got to have the systems to make the data available or not available to the attackers. In terms of privacy, it's more a matter of who's allowed to access the data. So it's kind of a subtle thing. You can think about it as external versus broad access to data. External in the sense that security is all about you let access either external or internal. So you're keeping the bad guys out. Whereas privacy is about who's allowed to touch the data. So for example, in your company, not everybody in your company can touch data that you've collected. If you're an e-commerce site, you don't let your whoever, your maintenance crew, your HR crew look at people's credit card numbers. It doesn't make any sense. They have to be isolated from that. And finally, accountability. They both have accountability for their own sphere. So, the security guys have to be accountable for security things. Privacy people have to be accountable for privacy things. So that's kind of the same thing. So in terms of privacy for things that are unique to it, it's broader. Kind of I just hinted at that now. Security is very binary. It's very black and white. Privacy is broader. So you have this whole thing of notice consent. We mentioned like these things that nobody reads. Those are notices, and you have to consent. This is the opt-in stuff. So that's all about privacy. Openness is you need to put on your websites how you deal with privacy. That's not a security thing. That's a privacy thing. What you do with the data. Relevance is about the data that you keep needs to be relevant to business things. You can't just collect everybody's data, which people used to do in the past. They just like, if you remember in the past, people would ask you like crazy things. You'd be like, why am I answering things about whatever, my date of birth, and I'm, getting some service that doesn't need it.
Question from the webinar.
Yeah.
Security is a lock, privacy is who has the keys? Maybe repeat the question.
Yeah, so the question is security is the lock and privacy is who has the key. I like that. That's a pretty good analogy. It's a little bit off in the sense that security has certain mechanisms like encryption. And so your security team will figure out who's allowed to like decrypt things. Privacy is a little, the place where it's a little bit off is privacy's broader in the sense that it deals with things about who is allowed to touch data within the corporation, but also some of these other things. Like proportionality, like relevance, I said, you can only collect, it puts kind of containers around data. It's not only just who, but it's the mechanism in privacy are about how do you control that data.
I've heard security people talk about zero trust. Is that in the overlap? Because it's both kind of security, but it's kind of a need to know. And
Yeah, that's a good point. Yeah, absolutely. So, so Greg asked, he's heard about zero trust. Is that something that fits in the overlap? And in general, the question is yes. Now, the thing is, this bubble picture shows up with different forms. If you go Google, like, you'll see Venn diagrams like this, and they'll have different things that are in and out because there's not a lot of consensus necessarily in all of these things. This is one picture, which I'll explain in a second, but proportionality is, it's similar to relevance, but it's essentially how much, what measures do you take, the measures that you take versus the data. So you have to take measures that are proportionate to the use of that data, the business use of that data. So it's very related to relevance in the sense that you have to, given the use that you're taking on the data, you have to put in place controls to make sure that it's not beyond that. Regional sensitivity, GDPR handles data or regulates data differently than CCPA. Content limits are things like data needs to be deleted after a certain amount of time. And so there needs to be, there's these things called privacy controls, which I've mentioned, which are basically the mechanisms and processes. And so written into the laws are things about data can be only kept for a certain amount of time. And in the past, people would collect data and they just like leave it on disk. They'd never like erase it, which is crazy. So this particular Venn diagram comes from this book that was mentioned earlier, the Privacy Engineer's Manifesto, which was written by my CEO. I was the technical reviewer of it. Okay, landscapes. Here's your eye chart. This is what security looks like. It is a huge industry. So there's different pieces of this, and you can download the slides and look at it, but kind of along the top, just the landscape here, up in the left-hand corner is data protection. This is, things that you do with the data to protect it, also firewalls, things like that. Compliance is a little stripe in the purple. Then you have identity management. That's, how you establish that you're you. Authentication. Application security is another area. But then kind of in the meat of the picture where a lot of the vendors are, to the left-hand side, are the operational things. These are things like incident response, threat detection. These are the things that your companies have to do security. It's like a massive area. And the right-hand side are more kind of towards the technology, the infrastructure. So network, protecting your network, the data center, the endpoints, et cetera. And then there's things like cloud security and IoT security. So if you really want to find the magnitude or get a feel for the magnitude of security, you can go to the RSA show in San Francisco. It's in June, and it's in Moscone Center, and it just fills Moscone Center. And if you go on the floor to the exhibit floor, it's just row after row after row of exhibitors. And this is where you get a feel for how big this map is. And this is like a huge industry. So privacy, on the other hand, is much smaller because it's newer. There's fewer players in it, and there's fewer areas as well. And so these are some of the areas that are covered. Data discovery, like what data do you have? And mapping is where is it? Consent, we talked about consent and notification. Data subject requests are like, I want to have my data deleted. Privacy impact assessment. Does anybody know what a privacy impact assessment is? Oh, good. You've suffered. Which side have you suffered through? Are you in privacy or are you on the engineering side? Oh, okay. So there's this thing that privacy people, basically it's usually a survey. And so they hand it to their product people and they say, tell me what privacy impact you have. And all the engineers hate this stuff because it's like, I don't want to fill this paperwork out. And it's not controllable. And I'll get to that. Our company tries to deal with this, actually. I'll talk about that a little bit later. Incident breaches, we talked about that. Risk management, if you have third parties that are involved with your products, there's risk involved. So that's the privacy picture. Now, AI saves the day, right? It's a silver bullet for everything in the world. Once we have AI, all our problems go away. So there are companies that are startups that are using AI to approach different problems in security and privacy. Here's just a smattering of them, just a few that are interesting, some of the up and coming ones. Cervelo actually detects abnormalities in railroad. Go ahead.
Say these startups, is this startups that use AI for security or privacy, or startups that help you do security privacy for AI?
Both. So some do each. And so the second part, there's some down lower in the slide that do that. Oh, sorry. So the question was, are these vendors ones that use AI to do security and privacy, or do they apply security and privacy to AI? And the answer is there's a mix. People do both. So we'll have some examples of both kinds here. So Cervelo detects anomalies on railways. So they're your friend if you ever take trains. Like they're looking out for problems in terms of security and in particular security. Eprius will look for drones and use AI to basically target things to take them out. The military kind of likes them. Obviously, security has military implications. This next one is very interesting. So Electronica has a box that they put in your manufacturing site or wherever that will listen to your machines. You can put in a data center as well and listen to, or basically figure out what's happening on the power in terms of this equipment. And so if it's a data center, if they start to see weird patterns of power, they can tell maybe somebody's crypto mining. It's very interesting technology. So basically they're not intrusive at all. They're like figuring this out just by the power fluctuations. Interesting. Key Zero uses LLM to do static security testing. That in the past, people have they've tried to scan through code with rules engines, and that only gets you so far. LLMs are nice because LLMs make up the rules essentially, right? So they'll learn what violations in code looks like. Nice. Private AI, they will skim out personally identifiable information out of data that you feed into LLMs. So if you're going to feed stuff into ChatGPT, it'll first, you feed it through their product, and it will find if there's any PII in there. And so you don't want to give your PII to ChatGPT, or most people don't want to. You don't want to give your social security number to ChatGPT. I hope you don't. So they have a product which will check it out. You know, what are you pushing through into ChatGPT or other LLMs? Transcend has a platform which is all about governance. So are you obeying the regulatory rules? And then finally, our company takes policies and runs it through NLP and creates tasks for engineering or IT or other business teams to perform to ensure that what is said in the privacy policy actually is done in your products. And that's one of the biggest fines that's coming out of some of the state rules. If you put something on a website that says this is what you do, despite the fact that nobody reads it, if you don't do it, you will get fined very heavily. Like if you say you do something and you don't do it, problem. Okay. So we're a little bit behind. So I'll make this kind of quick. So here's the LLM part. There's this great paper, which there's a link to it, that is a survey of privacy attacks and how do you deal with them. So I really, go ahead.
There's a gray box on the top. If you click on the X on the right, it'll go away. See your top blue box. There's a.
Thank you. All right. So it's going to run through all of these. I'm a little bit short on time, so I'll try to be brief. So I'll hit like just the middle boxes, but so these are the different types of attacks in privacy. Essentially, backdoor attacks are your data's been poisoned and it triggers activities that will make your LLM do things it's not supposed to. So you can do that in a data set. You can do it in the training set for a pre-trained LLM. You can do it during fine tuning. So some of the things that happen are you can release your weights, like a malicious actor through these backdoor attacks can produce an LLM, get it out in the wild, and then when people use it, like the actual use of the LLM is basically stolen. So they know they know what the weights are set, et cetera. And so they can kind of violate LLMs. Prompt injections, most people have heard of that. Essentially, if you have instruction tuning on when you're doing prompting, you can do two very interesting things. One is you basically can tell the LLM to tell it what are the prompts that people are giving you. So you're essentially stealing the input that the LLM is seeing. So that can be very valuable. Companies, when they use LLMs, what they use for prompts can be proprietary, and they keep it very closely held because that will end up, being value add for them. So these attacks will surface out what those instructions are. And then another thing which is more interesting is they can hijack your goals. So if you have an LLM that the results are like binary, is this like malicious or not? They can actually flip the goals or modify the goals so that the LLM is doing not what it's designed to do. It'll in some cases say something's not malicious when it actually is. And some of these attacks can be very targeted. In fact, there's a case, this paper is just chock full of these cases, but there's a case where in the embedding vectors, this attack just changed one embedding, and it actually changed the functionality of the classification engine. So it's just like one piece of data that's fed in to define the data set changes the manner of the LLM. So these things are pretty crazy. So membership inference attacks are pretty interesting. So if your LLM deals with data that's of a certain format, like phone numbers all have the same format. Social security numbers all have the same format. So if you know that somebody's dealing with these things, you can start asking the LLM to look for things of this specific format and see what it'll give you. Actually, GPT-2 would give you social security numbers if it had them, because you asked it the right way, the right magic words. And actually, with GPT-2, if you gave it like the verbatim instruction, like the set of things that lead up to asking for a security number, then it would just give it to you. But that implies that you need to know what those definitive things are. There's been additional work where they don't need to know that. They can still get at, just because of the format of the data, they can pull things out. So they don't have to sort of trick the model directly into getting it out. It can basically ask for it. So that's membership inference. Training data extraction is another kind of attack. Those are kind of interesting because there's different ways that you get into them. So one way is you can, in your prompt instructions, you can give conflicting goals. This is kind of like the old Star Trek thing, or maybe 2001, where you confuse the robot into self-destructing, right? Because you give it confusing goals. And as a result, it'll start to dump out information that it shouldn't. Very interesting. And then there's another thing where if a LLM does not generalize well enough, so it's like overfitting its data too much or close to overfitting, then you can force it to start giving very precise data out of it because it's too tight. It's not generalizing.
Specific.
Well, exactly right. And so you just hit it on the nose. These attack works because LLMs, in a sense, memorize things. And the tighter they memorize things, the easier it is to attack them because you can extract data out of them. It's just like the format. Like this format is a very rigid thing. They've memorized what that format is. Attacks with extra information. There's a couple different kinds of these. In the interest of time, I'm going to try to keep going pretty quickly, but some of them that are very interesting are embedding inversion means you figure out what the embeddings are for a model, and then you can just take off with it. Like you can suck the data right out if you know what the embeddings are. So that's another kind of attack. Gradient leakage is the same kind of thing. If you're stealing the gradients out of a model, you can go backward and get, both of these cases, you can get the exact input that users have put into the model. So you're like, you're stealing the data that's been put into these models. So there's some other types of attacks. Prompt extractions, you're pulling prompts out. Side channels, you're looking at stuff that isn't directly into the prompt mechanism. You're looking at things like, can you filter the queries or the data that goes into the training set, or process the inputs and the outputs in ways that will get you access to the data. Adversarial attacks are interesting as well because most machine models are not as robust as people would like to believe they are. So I came across this situation a few years back, and it wasn't an LLM, but it's of the same ilk. A Microsoft researcher demonstrated this thing where he took, this is image processing or computer vision. He took an image of like a tiger, and everybody in the room is just like, oh, that's a tiger, right? And then they ran a a digital signal processing algorithm on it, and they just twisted some of the bits. Same thing, it looked just like a tiger. So he showed it to people, everybody was like, that's a tiger. Well, the LLM in the first case said, you know, this is a tiger, 80% probability. That's pretty good. Afterwards, it says, this is a baboon, 50%. Like that was its best hit. It was totally fooled by, it's the instability of the model itself. So this is one thing this is why LLMs, you can't put your faith in these things as much as people do. So you have to understand how stable they are. Okay, so those are attacks. So that's like the fear and the loathing, right? So with a few minutes left, I'll tell you about ways to fix this stuff to a certain extent. There's a lot of work going on here. So differential privacy is a very interesting idea. It's actually mathematically based. And so you can actually prove these results. And essentially what you're doing is you're introducing random noise into the data that you use to optimize algorithms. So when you run an algorithm, you're running it through your neural net. And typically towards the last phase, yes?
Just want to let you know, you can go well past 8.
Oh, okay. All right. Well, I'll be under control. So I only have a couple of slides left. So
A question from streaming.
Yeah.
Can differential privacy help prevent some of these adversarial attacks? How often is it used in LLM training?
yes. So the question I'll answer, can differential privacy be used in some of these adversarial attacks? And I think there was a second part that I missed.
How often is it used in LLM training?
How often is it used in LLM training? Well, the answer to that is not enough, but yeah, I'll talk about that a little bit. So these are defenses, and you know, I started explaining how differential privacy works. You add in a certain amount of random noise into essentially the part of your model just before the output. And as a result, it can hide personal identifiable information. It kind of does the anonymization, which is back to the dog cartoon, right? Anyhow, so there's ways to apply it to pre-training, fine-tuning, prompt tuning, and the actual text generation itself. So to go back and answer your question, it does work fairly well. This DPSGD is differential privacy stochastic gradient descent, which is a way that models essentially achieve the results. And so you're applying differential privacy to different parts of it. So you can apply it to like the embeddings for the LLMs. You can also, when you're doing prompt tuning, you can apply it to the additional, so prompt tuning, you essentially add additional prompts into, you do it at the embedding level, you add additional prompts into your LLM to tune it better. And when you're doing that, you can control them with this differential privacy in the sense that you're anonymizing.
Question, if I have numeric inputs like pixels, I can imagine changing numbers randomly a little bit. For text, are you randomizing text? Are you adding spelling mistakes? That'll mess up the encodings and the semantic meaning.
So
How do you?
So you don't do it at the language level, you do it like at the embedding level. So remember, you put your embedding, like your embeddings don't know spelling, right? Your embeddings know kind of where you are in semantic multidimensional space, right? So it'll move things around enough so that you can't get back to the input data. So does that make sense? Go ahead.
So I want to just kind of understand this, but would this be something you would apply, for example, if you were building a system to do medical diagnosis and you were training it on loads and loads and loads of actual medical cases? And so you'd be trying to use this to get rid of
Yeah, so
information? Is that the idea of this?
Absolutely. And so,
Do the algorithms actually?
oh, yeah. I'm sorry. I
do
keep
the
forgetting it.
algorithms have to know which part is the privacy sensitive stuff? So like, would they need to know that they're looking for, names and addresses?
That's another
and
good
like
thing.
that
Okay,
before-
so let me answer that. Yeah. Okay, so the first question was, could you use this when you're doing like medical records and you're wanting to pull out personal identifiable information? And the answer is yes. So differential privacy is not just one thing. It's not just one algorithm. It's like a set of, they're essentially mathematical transforms. And so, in fact, one of the things that's very interesting is they're composable. Like you can apply one after another without losing the properties that you're putting into them. They're aggregating. And the other thing is you can stick them behind an LLM and take the output and apply it. And then anything you do after that won't defeat, like you can't defeat it after you've done it. Like whatever you've done afterwards will still be protected by the DP. It's like once you've done this, you're fine. So they will apply it before data goes in, apply it after data comes out. Sometimes they'll apply it to, as I mentioned, they'll apply it to the embeddings themselves. Sometimes, as you brought up, so the second question you had was, how do you know what data to apply this to? So you do have to have, like if you know, and so this will bring up something a little bit later, but if you know what your PII is, like the medical records, like what's private data, then you can actually apply the DP stuff to that data by itself and just train the rest of the model, and you'll get a good result. Against what?
Like DNA and RNA.
Yeah. Yeah. So, all right. So I'm gonna ask the question again because I'll beat Bill to it. So the question is, how do you use this in like genomics where it's like DNA? This is very specific data. So this goes back to the dog thing. It's like people rely too heavily on anonymization, which I'll talk about in a second too, but remember the idea is in these models, particularly the neural networks, I mean, that's what we're talking about for generative AI and LLMs. You feed a tremendous amount of data into it. And so as a result, you want to filter out the stuff that uniquely applies to an individual. And you can do that just it's like information science. By doing some tweaks and things like that, you'll be able to protect the data, protect the individual, but use the data in the aggregate. So it's like, I'm not even going to come up with an analogy because I'm tired, but there are ways to hide the individual. And I'm not even going to get into this too much, but one of the things that's happening now is there are areas like that where you want to know what's going on with the individual because you're doing medicine. So you want to know how to treat an individual. You don't want to be like fully anonymized because you need to know what that individual. So now they're like, there's this kind of wrestling match between, I want to anonymize everything, which the privacy people a few years ago were saying that's the answer. It's not, because the real use of some of these algorithms is to be able to identify precisely what is the issue that some person has with their health. So there is kind of a tug of war. And we'll get to this a little bit later too. You're asking great questions, by the way. Everybody is asking great questions, and you're kind of feeding you're feeding up things that are coming afterwards.
I was gonna,
Actually, she's got a question first, and then
DNA data and genetic, we're talking about access controls, right? More than privacy. So we want to have control who has access. to it.
Yeah.
So
So,
we're kind of mixing
well, so kind of,
it. We know control who has access to it, data, like their role and the competence of the organization. So we're switching back over to security, control access control.
right. And I mentioned that earlier on privacy. That's a very much a privacy thing. And also that's actually there is overlap there with security too. You want to control, the question was in healthcare, you want to be able to have, there's access controls, which who accesses the data versus like kind of munging with the data. And so, right. So the answer becomes security in the sense that you want to button down who has access to this. Well, actually, this is where they overlap because privacy is about who has the access to it. Security is about like whether they can encrypt it or not. So, but this is where they overlap. But you're right. Fundamentally, you're correct. Yeah. So, but to the earlier point, when you start feeding this stuff into models, then it becomes dangerous because the models have, and as Greg pointed out, they're memorizing stuff in a sense. So they're building in this information. And so you need to, one way to protect the model is like, don't let anybody use it, right? I mean, it's like, there's privacy and security have the same problem, which is how do you protect versus how do you actually use it? And so there's always this tension between buttoning things down too hard and usability. And so that's like the fine line that you have to walk. You have to figure out like, what are the measures you're going to take? And so this is where risk comes in. It's like, how much are you willing to risk, which like, it's a little bit of a scary thing. How much are you willing to risk with different things? Certain things you're just not allowed, you're not willing to risk at all, like your medical records, for example. Anyhow, you had a question.
I was gonna comment, speaker, about the genetic data. So one of the lines on there is federated learning, number 3. So if you're training from a lot of sources, what that'll do is that'll kind of mix and decrease memorization. So, and another thing is, if you're focusing on a particular task, like my dad had skin cancer, my mom had skin cancer, I have skin cancer. If I go to you and you're checking my genes, the neural net just needs to know if it matches the skin cancer feature. It doesn't need my entire genetic string. It's kind of the need to know for the problem. And so the federated learning and all other things will help with that.
Yeah. So I should have covered up the lower part of the slide. Anyhow, that's fine. So we'll get there. One of the things about differential privacy, which is a little bit of an issue, is it's a worst case. Like because of the mathematics, you're being like way too stringent than you necessarily have to be. But it's all right. It's like what we have right now, and we'll use it. So earlier, somebody asked, like, how often is this used? It's very common outside of machine learning. Like people have been using this for quite a while. In terms of LLMs, I don't know how wide it's spread. I don't know the answer to that, but it's certainly, I mean, this came out of a research paper. This didn't come out of like industry practice. And it's relatively recent, like it's like within the last 6 months. It's a survey paper. So there's a lot of papers that went into it, but so people are aware of it and they're working on it. And it is being applied. But it's probably not being as applied as much as you want. In terms of like our company, we're always surprised sometimes, not always, but a lot of times we'll be surprised on the extent or lack of extent that people go to keep private their data. And sometimes we'll like, we're not going to work with you. We'll go to customers and see what they're doing. They're like, there's ethical problems here that like, we don't even want to get involved in. Anyhow, question here.
It's a comment.
Yeah.
I think one other challenge that I've seen, I've been talking to some companies. A lot of the adversarial attacks have an assumption that you can access the training data and perturb it in a way that the output is imperceptible to you. However, as far as the model's working, it's not working fine. So a lot of the Fortune 50, 100 companies, without naming names, will say that our training data is so tightly locked down, nobody can access it. Now, is that a data integrity issue, or is that what if somebody does? And I think right now, going back to your regulations thing, because there's no regulation that's forcing people or these companies to tell you if there's a breach that has happened or not, they're like, it's fine, it's locked down. The privacy world, after the regulations came out, it was easier for, now I used to work for a privacy company, it's easier for us to cross that barrier. So I think the AI world is waiting for these regulations to enforce these companies to reveal when an attack is, that's when, you know.
Well, yeah. So it's just like the fines. It's like, until somebody shows up at your house and says, you owe me money, you know, you're not going to think about it, right? Necessarily. I mean, unless you're an outstanding citizen or something. I don't know. After you spend enough time in security or privacy, you get a little bit jaded, but there's hope. So that's differential privacy. It has its merits and it has its uses. It does have its limitations because it can sort of handcuff the models to a certain extent because it can be too rigid. Secure multi-party computation. So this and federated learning are related in a sense. So what the secure multi-party computation, SMPC, what they do is they use a crypto technique so that when people collaborate on feeding data into a model, you can unlock the data that you put in. So your data goes in and no one else knows that, can see that data, and vice versa. So everybody who feeds data into this model basically has cryptographically protected it. So it's a good way to allow people to work on a single model. And there's still work being done on this as well. There's two things that have to be done that make it challenging. So one is, well, there's two ways that they approach it. There's a specific challenge, which is the last layers of, or well, it's not necessarily just the last layers, but certain layers in neural networks are nonlinear. And these SMPC approaches require linearity. So in other words, like polynomial approaches versus, you know, something that's nonlinear equation or function. So all of a sudden it's like, well, we can't use this for anything that's got like a nonlinear function. Well, all neural networks have nonlinear functions in them. So what you do is, there's two approaches. One is you create a function that behaves like a nonlinear function. So you create your own version of softmax, which is a famous nonlinear function, and it approximates softmax sufficiently well that you get the properties that you want. So you actually alter the model's architecture. That's pretty cool. I mean, and accuracy wise, you do, it's pretty on par. The other thing that they do is they actually go into the primitives of the pieces of the model itself. So I was talking kind of about the layers. within the layers, there's different operators that you use, like things like indexing data sources, like a database, or just plain division. And so what they can do is they can create alternate algorithms that have at that level, at this sort of like nuts and bolts level, that have these good properties, this SMPC property. And a lot of times what they do is they use a piecewise polynomial curve instead of the non-linear function. So now I'm probably like, this is like probably too much stuff, like probably in too deep, but anyhow, go ahead.
But I'm just kind of clarifying. You say they train up the model on a bunch of data, and then afterwards, they go in and they replace the nonlinearities with linearities and do an optimization, and through that process, they get it to basically obscure the personally identifiable information.
So the question was, do you run the model first and then do these operations? And the answer is no. You actually alter the model with these operations, whether it's layer wise or whether it's the actual specific operations, and run the model then.
Train the model.
And train the model on that. So you're actually modifying the model itself so that it has this nice property. And the accuracy is good. And the accuracy, there's work that needs to be done in this area, but the results have been good. Federated learning. So this is more about, the solution to this is you have multiple models and everybody puts their own data into the multiple models and then they cooperate. And so in that sense, you don't have to display your data. You've got multiple models that are working together. And so there's different flavors of this. And it turns out that if you do that and you use LoRa fine tuning, which is a fine tuning technique, it does extremely well. It's one of the best ways to kind of hide your privacy information. So it's a pretty good step. Then those are all general approaches. There's some specific defenses against some of the attacks I mentioned earlier. This is my last like in-depth slide. I think my conclusions after this. So yeah, we're close. So this backdoor attacks that I mentioned, with this poison data that triggers off bad stuff. You can actually cluster the results from your model and begin to see like outliers, like anomalies in their results and say, oh, that doesn't look right. Like that looks like somebody gave me poison data. And this actually works pretty well. So it's like a machine learning model looking at your results, a clustering model, and saying, oh, here's an outlier. This doesn't look right. And another thing you can do is all models have this thing called a loss function, which determines how close the model is to the actual answer. The actual answer, if supervised learning, so that you know what the answer should be. If your model exhibits very high losses on particular parts of your data, then you can track those back to poison data. So that's pretty interesting as well. And then data extraction, the data extraction attack I mentioned, where you're, pulling data out from the training or whatever. They do like this thing where they figure out attacks and then defenses, and that's how they come up with the defenses. And then they'll do things like edit the weights of models to make them more robust against these attacks. And there's algorithms for the safety field, which is a field about, you guys have probably heard about this. It's a safe use of whatever technology you're using, but safety in LLMs. Those algorithms have bearing on data extraction as well. And then there's reinforcement learning with human feedback and reinforcement learning with artificial intelligence feedback. So these are types of AI that can allow you to detect the bad data. So,
Two questions from online.
okay.
First, do multi-agent workflows introduce new privacy challenges? And what are the specific considerations in managing sensitive information within these systems?
So the multi-agent workflows, that's interesting. So, oh, I should have like a post-it right here, right?
I'll print one for future.
All right. Yeah, if you guys let me
Yes,
speak
that's-
again. So the question is, what about multi-agent systems? Where essentially you're running different models that have impact on the final answer. And the second part was,
And what are specific considerations in managing sensitive information within these systems?
yeah, so multi-agents are pretty kind of recent thing in terms of machine learning. And this kind of work, I haven't seen references to it. I'm not an expert in this area, but I haven't seen references to it. But in that case, things like federated learning, in essence, would help you out there, because if you're essentially able to isolate the agents from each other in terms of the data that they're training, then you get the federated learning effect. So I think that's probably how it'll be done. Okay.
And then Tony asked, can you elaborate more on how to distribute LLMs to protect data? Can't other callers still reverse engineer to extract training data weights, even if the model runs local?
So okay. So yes, so if you're, in fact, some of the, like, there was one of the papers that this referenced, like, it could basically pull your model out. I didn't actually describe it. It was in that big diagram. The last thing was like stealing a model. If you know how to trick the API effectively, you can actually get the hyperparameters and the algorithm itself. So it's kind of, it's theoretically it's possible. Yes. The answer is yes, in theory. It's up to the people that are building these systems to be able to prevent that. That's why you've got to start applying some of these approaches, so that if you're going to open up your API to the world, it will be attacked. So you need to start, applying these things. And so that's why when people rush to put models out, it's a dangerous thing to do. So a very good question, and it points directly at what people need to do in practice, which is you need to apply these different security measures, security and privacy measures, so that if you make your models public, that they won't succumb to attacks. So I think that answers the question. Okay. So last but not least, RAG, which Greg mentioned earlier, which is all the rage. Every AI conference I go to, like, everybody's talking about RAG. It actually has this really great property. So briefly, what RAG is if you've trained a model and one of the reasons why this came up, and it's a great sort of side effect, is if you have a model and like ChatGPT 3.5, like, it only knew the world to a certain date. When it was released, it didn't do any training after that. So you can ask it questions about like, you know, who won the World Series this year? And if it was trained 2 years ago, it won't know. It doesn't know. So that's a problem with LLMs. Like, they're only trained up to a certain point before they're released. So one way around that is you actually you give it factual information, you store it typically in a vector database. And so when you ask it a question, you do queries into that database to add information into the question, and it makes the question more valid. And that has a lot of good effects. One is it brings your model up to date, as long as your vector information is good. And it also can help cut down on the hallucinations, because the vector information is real information. So in theory, it should allow fewer hallucinations, because the model will, like, it's got more information. So particularly the information that's coming from the vector store, which is factual, it should cut down on having the model go off into the weeds, because now it has information that's real. So if it didn't in its training, you've given it sort of an injection of truth, right? So, so the cool thing about the RAGs, in a sense, is if you kept your sensitive data in the RAG, then, and you gave people the LLM, they would never see your sensitive data. It's not, the LLM's not trained on the sensitive data. Your vector store is, and you protect that vector store like this is your gold. So that's actually one kind of interesting side effect of this whole RAG world. And this is a huge area of research right now. People are, I mean, it's like everybody's working on it, and they're finding out new ways to make it more effective, because even the RAGs will hallucinate. Occasionally the vector database is like, it's garbage in, garbage out. If your vector database isn't good, then it's not going to help. So anyhow, so conclusions. I told you I'd get there. Okay, so from the bar charts, security has massive impact and privacy is on the way. And it already has massive impact. It's just like the laws haven't caught up to it yet. So that's what all those bar charts were about. Startups are using AI to save the world, but it's a big thing. LLMs have new challenges, but the defenses are showing up. Some of the ones that we've known about, like differential privacy, apply in this case, and there's new ones are being created. And then there's a lot of stuff to be done. And these are like, these came out of this paper too. If you're into this stuff, I highly suggest this paper. But some of these talks are a little bit pathological, or some of these attacks are pathological, like getting a hold of somebody's embeddings. Like, that's really hard to do. Like, if some company is building models, getting a hold of the embeddings that they've done is pretty hard to do. So some of these attacks, like theoretically they're possible, but to actually get into a company and pull them out, it's pretty hard. So the call is for what's actually really going on in the wild. Like, what happens when real attacks are going on, and how effective are some of these things in for real? So this other thing, which is kind of interesting, privacy aligned to human perception. So if you start using these models to write fictitious things, I want to use my model to write a novel. So I have like fictitious characters doing fictitious things, hopefully benign things, but the privacy could say, this is not good. These things aren't real. Like, we're not going to let you do this with this model. And so again, this is kind of the tension between like that security faces as well. It's like, is your privacy so buttoned down that it begins to prohibit the use of what you're actually doing? So, I mean, that's a funny example, but it's kind of true. If your models determine that a lot of things that these models do that are protecting things, like the one that protects the stuff that goes into ChatGPT, they do a thing called named entity recognition or entity recognition, where they're figuring out who the entities are. And so if you've like nailed down your privacy so hard, whenever they see entities, if they're like, this doesn't fly, then it's gonna make this stuff impossible to use. So that was kind of a vote for reality. And then context is everything. In the ML world, you always say something is everything, right? So, or is all you need. I should have said context is all you need, but anyhow, it's kind of an inside joke. But some of these defenses are based on particular things that are fed to the model. So for example, you asked a question about how do you know which pieces of data to run against DP? So you may know ahead of time, but if you do that, when you feed these whole things to a model, the reason why these LLMs are so successful is they understand context and they can piece together context. So this goes back to the dog thing, where as soon as you connect the internet, you start to give away information. And these models can correlate things incredibly well. So given enough context, some of these defenses that are like very specific to the pieces of data, they're missing the context. And the models will be able to fill it in, essentially, connect the dots. So that's kind of a warning. Anyhow, so that's what I've got. I'm open to more questions. I hope there was something for everybody. It's hard to go high level and deep at the same time, but I don't know. Anybody have any other questions, or I hope it was useful.
Two slides.
Mm-hmm.
You have the attack.
Where's my cursor? Oh, there it is. This one.
Just only two of the slides.
The defenses?
Yeah, oh, yeah. That,
Yeah.
on the backdoor attacks, saying that person samples detected by highest loss. I want to know, how do you define loss?
Oh, yeah. So this is so loss is a machine learning thing. So the way that, just very briefly, the way the neural network works is you feed it. I mean, it's a statistical model, and you feed it through what are called layers that it's a network that gets optimized. The more data you feed it through, it configures itself to do whatever task it's designed for. So if you're like doing image recognition, then you feed it enough data, and now it configures itself to recognize the difference between a cat and a dog picture, right? I mean, that was the original big wow. But so when you feed data through a neural network and you're training it and you're getting it to learn, you feed it through, and then if you know what the answers are, like the cat and dog thing, like when you have a piece of data, you know ahead of time, it's labeled. It's either this piece of data is going to give us a cat or it's going to give us a dog. And that's a pretty simple example. But the last thing that you do in a neural network is you say, how right was I? And so with like the binary things, it's pretty clear. It's like, but it's also probabilistic. So, I mean, there's probability involved. Like, it's like I said, it's like 80% a tiger. And Yeah, it's how close to the actual answer you are. So, I mean, there's probability underneath it, but you can just think about it in terms of how close to the answer you are. And so then that's fed back through the network, and the network adjusts its weights. And because that's why you push so much data through this, like you push it through is what?
The word loss.
Yeah. So the loss is just a matter of how wrong the model is at any given point in time. Because as you train it, like hopefully the loss gets less. And so, so when you feed it data that's never seen, so after you've done the whole training thing, you've got your whole network configured. That's training. And then you do inference, which is when you actually are using it. So, okay. So now I'm using cat and dog is a very kind of simple thing, but even then it's going to give you probabilities. And it might be better to look at a classification where it's like multiple animals, but so what comes out is essentially the degree of how wrong the answer was. And so for each thing that you feed through it. So like I mentioned before, this weird thing where it turned out it was like a given 50%, like the loss is off that's incredibly high loss because like it was supposed to be a tiger, right? So the loss in the original case, it's like 80% good. The loss is around 20% or something, right? So you're trying to train it so that that loss is less and less. And then, so what happens when you feed through data that's been poisoned, the losses may go way up because you've fed it something that is like nonsensical, so to speak. Okay. So, I mean, in that, I should have gone back to that tiger example because they perturbated, because they changed the, oh, you got it. All right. All right. Oh, yeah. Yeah. The loss is just a measure of like how well the model.
Maybe one last question before we wrap up.
Oh, there's one behind you. So, yeah. 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 So each slide, it was in kind of a pale blue. Each slide that references, there's a link for each slide has a link in it in terms of where the information came from. Except for this one doesn't, this one's related to the previous slide. It all comes from that paper. So, yes.
So maybe by tomorrow you'll have the slides posted, or what's a reasonable timeframe?
What day is tomorrow? So, I'll have it by the end of the week.
Okay.
I'm in a conference the next 2 days, so, yeah, I'll try to get it up as soon as possible. If I have to do it on the weekend, I'll do it on the weekend, so.
Sure.
Okay. All right. Does anybody, oh, you said one more question, so. Yeah, I'm free to talk afterwards, so if you want to chat afterwards, I'm happy to do that.
Thank you. Our next talk is same time, Wednesday next week. It's gonna be about medical LLM kind of discussions, dialogues. And then also we're planning, we'll probably have another class in May. That's like the one we did in November. That'll be kind of drag and reason. So we bring one for the generation. And then some of the reasoning methods that can help improve your, so that'll be like